Good morning, physical science students. Today we are doing our second lesson on motion. We are continuing our discussion of Standard 8, specifically looking at Standard 8A and focusing on acceleration today. So yesterday was speed and velocity, today is acceleration. Oops, here we go. So what is acceleration? Acceleration is a change of velocity. So acceleration is a rate of change in velocity. Acceleration is both a rate of change in velocity and can also be in the direction that the velocity changes. So it is a vector measurement. So it means that if an object's speed stays the same, but its direction changes, we consider it to be accelerating or deceleration. So you can have changes in acceleration one of three ways. You can speed up, you can slow down, or you can go around a curve. So in terms of terminology, if we are speeding up, our velocity is increasing, and that will result in a positive acceleration. Oops, tablet's upside down. So positive acceleration. So if we are slowing down, we have a decrease in velocity. We are moving slower, which results in a negative acceleration. And if my velocity stays the same, but we change our direction, notice that this object is going around curves and going around a circle, it is considered to be accelerating. It's not necessarily positive or negative, its direction is changing. Now we can have a small acceleration that's a gradual change in our speed, or we can have a rapid or large change in speed. So positive acceleration, as I said, is an object speeding up. Negative acceleration is an object slowing down. So yes, you will deal with negative numbers in physical science. So if an object travels in a straight line and the acceleration is just the change in speed. So if we're just moving forwards or backwards or up and down, if we're not making any kind of turns, the object's acceleration is the change in speed. But if the object's acceleration is in the same direction as the velocity, then the object is going to speed up. So if we are moving forward and we are adding additional force and we start moving forward faster, that's a positive change in our acceleration. So example, my person is on skates. They are going this way and we notice that they have a positive increase, or going to the right, an increase in their speed. That would cause the object to have a positive acceleration. If the acceleration is in the opposite direction, then from the way the object is moving, you're going to have the object slow down. So my person is moving to the right, but their acceleration is to the left. So each time you'll notice that the arrow gets a little bit smaller. That means that my speed is slowing down. We have a negative acceleration. So if you look on your formula sheet, you will notice the acceleration formula. That T did not format the way it should have. So acceleration is calculated by taking the change in velocity over time. It is important that you always do the final velocity minus the initial velocity. So final velocity is the speed at which we end at. Initial is our starting velocity. And time typically is going to be measured in seconds. When we're talking about acceleration, time is almost always measured in seconds. So sometimes instead of seeing the VF minus VI, you may see the equation written as delta V over T. And that delta V just means change in acceleration. So it's the same thing, written slightly different. Now remember that when you're using your magic triangle, when you're trying to plug it into the triangle, since the equation has this division bar, we have to show the division bar in the triangle. So we have to have the v over the t. The nice thing about the triangle is it lets you set up and solve for different types of problems. So let's say I have the acceleration, but I'm trying to find time. Well, it tells me that if I have acceleration and I have my velocities to find time, I would take velocity divided by acceleration. So I cover up the t and it tells me what I need to do. If I have my time and my acceleration to find the change in velocity, to find my delta v, I would cover it up and I can see that a and t are side by side. That means they would have to be multiplied to find the change in velocity. Now our unit for acceleration, because we're taking velocity, which is measured in meters per second, and we're dividing it by time, our unit for acceleration is meters per second, or meters per second squared. So when we have that squared symbol, that means there's seconds in consideration twice. So m over s squared is read as meters per second squared, and it means the same thing as meters per second. So that little slash means per. So when we're looking at doing the calculations, remember we're going to use this three-part approach. We're going to start by identifying our givens. We're going to figure out which version of the equation we need to use, and then we're going to plug everything in. Knowing that math may not be your strong suit, this three-part approach will help you with any problem. So first and foremost, find your givens. Your givens are the things in the problem that have numbers. If it's got a number or if it's got a unit, it's probably important. So notice this first number right here, right in front, says 10 meters per second. You have to know that meters per second measures a velocity. We don't know if it's our initial or our final yet, but we do know it's a velocity. We can also see the 32 meters per second. That would be our other velocity. There is also a number hidden in the words. Not sure why, but for this particular problem, instead of using the number 3, we just put 3. So 3 seconds later is telling me time. So we know our time is 3 seconds, and we know that we have our two velocities. And yes, they're labeled on my PowerPoint, but let's see how Miss Raines determined whether it was my initial or my final. So this 2 words will let me know. Starts. It's telling me that it starts at 10 meters per second. So that is a dead indicator that we're looking at that to be my initial velocity. The word later lets me know that the other answer is my final velocity. So this problem is asking us to solve for acceleration. That means we are using the equation as is. We don't have to necessarily use the magic triangle. Remember, unless you're using Desmos Scientific with a fraction button or one of the Casios with a fraction button, you're going to want to subtract and get a number before you divide. So VF minus VI all over T. Now, I use the parentheses in this layout, but with the Casio or the Desmos Scientific, you could type it into the calculator as 32 minus 10, all divided by 3. With the TI calculator, you'd have to use the parentheses, otherwise it would not necessarily do the orders of operations correct. You don't necessarily have to show this piece right here. You can. You're always welcome to show extra stuff, but at a minimum, I would expect to see for any calculations you're given, your equation, your work, and all the answers off the page. And your answer. Hold on one second as I fix the answer. Here we go. So handy dandy calculator tells me that it is 7.3. It is a positive value. And since I have ms divided by s, my unit for this answer must be my unit for acceleration, which is meters per second squared, or m/s with the little 2 at the top. So let's look at a second example problem. This problem, how long will it take the car traveling 30 meters per second to come to a stop if its acceleration is negative 3 meters per second squared? So we start by finding our givens. We find the numbers in the problems. First number in the problem is that 30 over s. That is a velocity. So notice how it's wording. It's talking about how my car is traveling at this speed. That means that is my initial velocity. It's asking us to find time. Whether you put time at the beginning of your list or the bottom doesn't really matter. So we can also see that we have another given, negative, I wanted to change the color, but it didn't work, whatever, negative 3 meters per second. That unit has an exponent. That is a dead giveaway that it is acceleration. So even if the problem doesn't tell you that it's acceleration, meters per second squared always means acceleration. So it's asking us to find our time. Well, in order to find time, we have to have VF, VI, and A. If we don't have all three, we can't find the time. We have the A and we have the VI, but the VF is hidden in the words. And this is one where it is really and truly hidden. So notice how it says the car comes to a stop. So a stop. If I think I am not moving, what is my speed? Well, anytime you're at a stop, your speed or your velocity is 0 meters per second. That can be something that you write in your notes as a reminder. If you're at a stop, or if you're starting from a still position, your initial or your final speed is going to be 0 meters per second. So stop can also be a number as well. And my acceleration. So we're asked to solve for time. I cover the time up in my magic triangle, and it tells me that I need to subtract and then divide. You don't necessarily have to show that equation separate, especially if you're using a triangle. Either version of the equation will work. I have no preference. I just want to see at least one version in your calculations. At least one version of the equation. Why are you not selecting? There we go. So it does not matter to me which one you use. So we're going to plug and chug. Final minus initial. It has to be 0 minus 30. 0 minus 30. Yes, that's going to give you a negative number. When we take a negative number and we divide it by a negative number, we get a positive number. So the time that it takes to de-accelerate or to slow down from 30 meters per second to 0 is 10 seconds. It takes us 10 seconds to slow down from 30 to a stop. All right. Example number 3. Again, use your 3-part approach. Find your givens, your equation, solve, and tell me your answer. So I always start with the numbers. Notice 25 meters per second squared. That meters per second squared is telling me that we have an acceleration. 4 seconds is a time. So we look at the problem and notice that it is asking us for the change in velocity. So change in velocity means delta t. So the top part of the triangle kind of just simplifies. I said delta t, I meant delta v. Delta v is what the top part of the equation simplifies to. We don't necessarily have to have an initial or a final because it's just asking us how much does the velocity change. So we cover up the top part and notice that this time we are multiplying. The other two times we had to divide because we were covering up one of the things at the bottom. But if we cover up the only thing on the top, that means we must multiply our two numbers. So 4 seconds times 25 seconds. Really, if I was doing it in order, I would have done 25 times 4, but it doesn't matter. You get the same answer. 25 times 4 gives you 100 meters per second. So the change in velocity is 100 meters per second. So maybe I'm going from 0 to 100 or from 25 to 125. It doesn't matter because we were just looking at the change in the velocity. So for today's practice, you've got a combination of a few practice problems, so a few speed, velocity ones, a couple acceleration ones, as well as some sorts. When you look at the assignment in Google Classroom, you'll notice the first couple of ones have some terms that I am wanting you to drag and drop into the appropriate locations. If you're having any challenges with this terminology or with the calculations, please come and see me at my open office hours. As always, I'm an email or a Google Voice Meet away. So if you've got any challenges, let me know, and I will see you tomorrow.